Hello class, in this lecture, as we discuss the fundamentals of fluid flow, this lecture tackles the flow rate, the energy and the head of fluid that is traveling inside a pipe. We will be discussing also here the efficiency of pumps and turbines, and the last part of this lecture is about Bernoulli's equation. So let's start. So let's define discharge, or also called as flow rate. Let's say we have here a pipe where fluid is traveling inside that pipe. We define the discharge or the flow rate as the amount of fluid passing through a section of a stream in unit time. So let's say this is your section of the pipe. So the amount of fluid that is passing through that section, which is the volume of that fluid per unit time, which is the time. Okay, so it means the amount of the rate of flow of the liquid inside the pipe is your discharge, or we can express that as the volume per unit time. So our symbol used for discharge or flow rate is Q, with a unit of in SI unit, which is in cubic meter per second, or in per hour per minute, depending on the required. Now, we can also define the discharge or flow rate if we have a given cross-sectional area of a pipe and the equivalent average velocity of the liquid that is traveling on that pipe as the product of the cross-sectional area and the velocity will be equivalent to our flow rate, because the area, given that we have a unit of square meter, and the velocity of meter per second, it will give us a value of cubic meter per second, which is equivalent also to the unit of flow rate. Okay, so either we have volume per time, or the discharge or flow rate is equals to cross-sectional area times velocity. So let's discuss Reynolds number. Reynolds number is one of the bases of the resulting value for the Reynolds number is the basis on to what type of flow that is present on a pipe. So Reynolds number has a formula of Vd over nu, or it is also equals to rho Vd over mu. So the velocity of flow is V, d is the inside diameter, rho is mass density, nu is kinematic viscosity, and mu is the dynamic viscosity. So depending on the value of the Reynolds number, we can identify what type of flow it is in the pipe. So we can say that we have a laminar flow when the paths of the individual particles do not cross or intersect. So let's say we have here a liquid passing through this pipe. Okay, so all the particles move on the same direction. Okay, they are uniform in direction. So by many careful experiments to commercial pipes of circular cross-section, the flow is laminar when the computed Reynolds number, or Re, is less than 2100. So using this formula, if we have computed less than 2100 for the value of the Reynolds number, it is laminar flow. On the other hand, we have a turbulent flow when the flow is said to be turbulent when the path lines are irregular curves and continuously cross each other. The paths of particles of a stream flowing with turbulent motion are neither parallel nor fixed, but it aggregates to forward motion on the entire stream. So the value for the Reynolds number should be greater than 2100 for it to be turbulent. Okay, so that's it. We have laminar and turbulent flow. Now for continuous flow, um, given that we have a pipe with varying cross sections, so by principle of conservation of mass, continuous flow occurs when at any time the discharge Q at every section of the stream is the same. So in a liquid that is flowing in a pipe that has a varying size or the cross section, the value of discharge is always the same at any point. Okay, so it means that at point 1, point 2, point 3, we have the same values for its discharge. Okay, so it will give us each value even though the cross-sectional area are not the same. Okay, their discharge are always the same. For incompressible fluid, this is our equation, and for compressible fluids, we just put the pressure. Okay, we multiply the pressure on the product of the cross-sectional area and the velocity at each section. So example number 1, we have to determine whether the flow is laminar or turbulent if glycerin at 25 degrees Celsius flows in a pipe with 150 mm inside diameter. The average velocity of flow is 3.6 meters per second. And given the mass density of glycerin, which is 1259 kilograms per cubic meter, and the dynamic viscosity is 9.6 times 10 raised to negative 1 Pascal second. Okay, so let's solve this problem. The given are the temperature. We have 25 degrees Celsius. The inside diameter of the pipe, that's 150 mm inside diameter. Average velocity V, 3.6 meter per second. Mass density rho, 1259 kilograms per cubic meters. Dynamic viscosity mu, 9.6 times 10 raised to negative 1 Pascal seconds. So let's solve this using the formula for the Reynolds number, which is equals to rho phi d over mu, since we have a given dynamic viscosity. So the given mass density is 1259 kilograms per cubic meters. The velocity 3.6 meter per seconds. Diameter 150 mm. We convert that as in meter. So divide 1000, that's 0.15 meters. 0.15 meters for us to have a consistent unit of meters on all the given values. And dynamic viscosity 9.6 Pascal second times 10 raised to negative 1. Pascal is in Newton per square meter. Okay, so that's Newton per square meter. Newton per square meter second. So if we still want to convert Newton, that's equivalent to kilogram meter per second square. Okay, so let's rewrite the unit of kilogram meter per second squared. So let's check what unit we will have in this problem. Okay. So based on the given units, all the units will be cancelled out. Okay. So we will have a unitless value for Reynolds number. So let's now compute. So just make sure that all the units that we use here in this equation are consistent, which is in kilogram, meter, and in seconds. So we have 1259 times 3.6 times 0.15 over 9.6 times 10 raised to negative 1. Okay, the Reynolds number is 708.1875. Okay, the Reynolds number that we have computed is less than 2100, which is an indication that this flow is laminar. So the type of flow of the glycerin in a pipe, in a 150 mm pipe, is said to be laminar. Okay, so that's how you solve the Reynolds number. Example number 2. Compute the discharge of water through a 75 mm pipe if the mean velocity is 5 meter per second. So given is the diameter of pipe, which is 75 mm. Mean velocity is 5 meter per second. So flow rate Q is equals to area times velocity. So area is equals to pi d squared over 4 if we have given diameter. But we have to convert mm in meters so that we will have an equivalent value of cubic meter per second for the discharge. So divide this by 1000. The diameter will be 0.075 meters raised to 2 over 4. So computing the area, cross-sectional area, that's 0.075 squared over 4. Okay, 0.0044. Or we can directly substitute that last here. Area, which is pi times 0.075 meter square over 4. Then we multiply that by the mean velocity of 5 meter per second. So the answer is equals to 0.022 cubic meters per second. Okay, that's the discharge. Next, the discharge of air through a 700 mm pipe is 6 cubic meter per second. Compute the mean velocity. So this time we have a given discharge Q, which is 6 cubic meter per second. The insert diameter of the pipe is 700 mm. Compute the mean velocity. So again, Q is equals to AV, but what is required is the velocity. So divide both sides by area. So we have the velocity of Q over A. So we can directly substitute the values here. We have 6 cubic meter per second. And for the cross-sectional area, we must convert first the diameter of this pipe, which is in mm. So divide by 1000, that will be 0.7 meters. And for the cross-sectional area, we have pi d squared over 4. Substitute that here. We will have d of 0.7 meter square over 4. So we directly calculate that. We will have 6 over pi times 0.7 squared over 4. That's 15.591. 15.591 meter per second. So unit is in meter per second for the velocity. Okay. Next problem. A pipeline consists of successive lengths with diameters of 390 mm, 310 mm, and 260 mm, with a continuous flow through the line of 300 liter per second of water. Compute the mean velocity in each size of pipe. So we have a pipeline here with different diameters. We have 390 mm for largest pipe. This is 390. It's the diameter. And this diameter of this one is 310. The smallest diameter 260. Okay, diameter 1, diameter 2, diameter 3. Let's determine here the mean velocity on each pipe. So what will be the velocity here and the velocity of the smallest. Okay, so again, using the principle of conservation of mass, the mass or the flow rate on each section are equal because of course the amount of water that will be traveling from here is just the same. All of the water particles that will travel on the largest pipe up to this point will just be equal. So all of the flow rate are equal, making an equation Q1 equals to Q2 equals to Q3. It means that their values are 300 liter per second. Okay, so given the diameters of each pipe, we can determine the cross-sectional area, and we can also determine its mean velocity on each pipe. After that, we can compare how proportionate it is, the velocity with respect to the cross-section. Okay, so given the flow rate of 300 liter per second, let's convert that first to cubic meters per second. So conversion factor for 1 liter, okay, to cubic meter is that for 1 cubic meter, we have 1,000 liters. So it means to convert this to cubic meters, that's to be divided by 1,000. So we have 0.3 cubic meters per second for the value of discharge. So for Q1, Q is equals to AV. So the area at the first section and the velocity. So the velocity is Q1 over A1 or just Q. So Q is 0.3 cubic meters per second over area 1. So the area, if we have 390 mm, so pi d squared over 4. That's 0.3 cubic meters per second divided by the diameter is 390 mm divided by 1000. That's 0.39 meters square over 4. So the velocity is 0.3 over pi d squared over 4. That's 2.511 velocity in meter per second. That's the answer for the first or the largest pipe. For the velocity at the second pipe, V2. So let's just derive that from Q equals to AV. V2 is just equals to the flow rate over the cross-sectional area. So the flow rate is just the same, which is 0.3 cubic meters per second over cross-sectional area. Let's just substitute the diameter 310 mm, convert that to meter. That's pi d squared, 0.31 meter over 4. So let's just change this to 1. Okay, that's 3.975 meter per second. For the velocity on the smallest pipe, we have Q3 over A3. 0.3 cubic meter per second again, to be divided by the diameter is 260. So pi d squared over 4, 0.26 meters squared over 4. The answer is, let's change this to 26. The answer for the velocity is 5.65 meters per second. Okay, so here are your values. So as you can see, based on our calculated values, the velocity increases when the diameter is decreased. So it means that the diameter are inversely proportional with respect to the velocity. So when you increase the size of the pipe, the smaller or the slower the velocity in the pipe. But when you decrease the diameter of pipe, we will have a larger value of velocity. So that principle is used usually when we use it on our garden hoses. Okay, so on our garden hoses, usually we cover some part of the opening of the hose for us to have a stronger discharge on the hose. So it means that because when we decrease the value of the opening of the pipe, the tendency is that we have a smaller value of the cross section or the diameter, and it will result to a greater value for the velocity. So in this principle, we have already applied this conservation of mass. Okay,